Welcome to the shop. In today's video, I'm continuing NQALHA production run number 4, making 10 units. Each unit has 75 parts. So that means I need to make 750 parts. I better get busy. The part that I'm making today has a number of interesting challenges and interesting features that during prototype development I discovered some ways to make it wrong, and now the procedure and the toolpath have been corrected to make the parts more accurately. I start off by cutting the aluminum extrusion on the table saw. Now, for many of my parts, the chop saw is just fine. It produces a nice cut with almost no burr. For this part, the way it's clamped and fixtured and just the overall process of constructing it, the table saw makes a much better cut. So it's off to the table saw. This is a high quality table saw. It's very rigid. I've got a specially designed thin kerf aluminum cutting blade that does a really excellent job. Also down here, what you can't see in the video, I have a digital readout on the fence, so I can get some pretty decent accuracy. I mean, it's not a machine tool, but actually works quite well. So going to be cutting the stock here is 1 by 1.5 inches 6061 aluminum, and okay, that's correct. I had the DRO set for incremental mode, and it was giving me a really bogus result. So I'm going to just clean up the end a little bit here using WD-40 as a cutting lubricant. And of course I'm using, because this is a fairly small piece I'm making, I got to be really careful. I got to pay attention. So I'll probably stop talking a lot while I'm doing it. And before going on, I use push sticks for everything for safety, and they're always made of wood. I never use metal push sticks. And my push sticks all have a long protrusion. I know that some people use a shorter protrusion, and I do too on some parts, but for many of my things, I like the fact that I can apply a downward force at the front of the push stick to keep the piece even more under control. So I haven't had a problem cutting aluminum on the table saw, but I need to pay attention. I need to be careful because things can go wrong very quickly when cutting aluminum on the table saw. The table saw gives a nicer surface finish and better dimension and better perpendicularity than the chop saw. And that's even with, this is a fairly dull blade. If I had a freshly sharpened blade, I think the cut quality would be even better. that concludes the table saw operation. I'm going to just knock the burr off the blank here, and then talk a little bit about why this part is challenging. So this part is going to have a hole drilled through it perpendicular to this face, and the hole needs to be, it's going to be a reamed hole for a bronze bushing that provides the stability of the head and the twist axis. And a small deviation from perpendicularity in this hole relative to this face is magnified by the geometry of the head, resulting in fairly serious dimensional problems at the edges, and in extreme cases can result in rubbing. And I discovered this during the prototyping of the thing when I was developing it, where I put the critical reference face down and drilled the hole from the top, and for one reason or another the vice jaws weren't perfect and something, you know, whatever. The base was not precisely perpendicular to the hole, and it was off by just a fraction, but because of the distances involved, because there's a short distance here and magnified by a longer distance where it screws to, it ended up resulting in misalignment and errors. So I redesigned the tool path and the setup and the fixture. So now I put the blank in the vise, and let me go and do that. So the blank goes in the vise. I take a 1/2 inch end mill and skin the surface. I'm using the ledge of the soft jaw as the Z0 reference, because the material, even though it's nominal 1-inch material, I don't know what it really is, it's whatever. So by skinning the top surface, I get better dimensional control, and I get somewhat more guaranteed flatness, although the extrusion is pretty darn flat. So I skin the top surface with a 1/2 inch 3-flute end mill, then with the part in the same in the same vise, clamped in the same position, drill and ream the critical diameter hole. Then, moving over here to work offset 3 in the left vise, I made a tooling plate with a pin that's precision machined to fit the reamed hole nicely, so it indicates on that pin, and then there's 2 mounting holes that are used in the design of the part, and the mounting holes go into the tooling plate. Z0 is set on the surface of the tooling plate like it always is, and you notice that I made the tooling plate a little bit long so I'd have room to put the tool setter. So once again, this is a known trusted tool path that has made parts before, and I believe it is correct, but I'm going to treat it as a new tool path and just be careful through the first cycle. Work offset 1, G54, standard 0, single step mode. Observe that, oh, and that, boy, that 1/2 inch end mill really flings the coolant. Boy, oh boy. Let's try to reduce the spray a little bit. My enclosure could have been maybe a little taller, and maybe someday I'll put an extension on it just to keep the coolant spray off my keyboard. So Pre-feed looks correct, 1 inch above the surface. Finger on the stop button. Into feed position, looking correct. And everything looks like it should be correct. I'm just doing a pocketing operation, skinning off about, I don't know, 50 thousandths or so, not much. Now, gonna be cutting a ledge, and this is a clearance ledge because when it's in place on the NQALHA, there's a couple of potential conflicts. If I just left the block the full size on that face, I'd be running into other things. So this is a bit of clearance that appears to have been cut correctly. So next operation coming up. And sure enough, I didn't load that tool. So the system tells me on the screen what tools I need to load, and boy, I sure have been making a lot of mistakes ever since I started doing video, forgetting to load tools. So single block, pre-feed correct, looking good. Since this is a small diameter drill that's going to be going through 1 inch thick of material, I'm using a full peck cycle to guarantee that I've got the chips clearing and not getting caught. It's also a stubby drill, and I'm checking here with the old eyeball just to make sure that I have enough stick out, and yes, in fact, I do have enough stick out. Coming up with a compromise on the nozzle is kind of a trick. So that I was going to say that completes it, but I totally forgot my big hole. So single block, pre-feed looks correct. Feed looks correct. 2,500 RPM, 15 inches per minute. Fast peck cycle, which looks to be completely correct. Coming up on the reamer now. Pre-feed looks correct. Feed height looks correct. As I said before, I ream the holes that are going to get bronze bushings because getting a nice tight press fit on the bronze bushing is really important. I don't want my bronze bushings pulling out as the machine is used. So that successfully completes the operation, and now I've got a reamed hole perpendicular to a milled face, which has been proven to result in the accuracy that I need and works exceptionally well. So now I'm going to move over. When production gets going, I make what I call a combo tool path. that does the first operation and the second operation with a blank in one vise and then the first operation part in the second vise, but for validation purposes, just to make sure that all is well, I'm going to go ahead and run the tool path separately here. It also kind of speeds up the video, and I know I make long videos that can maybe be a little more boring than some would like. So I'm going to index from my precisely drilled hole. So the way the geometry is going now, I've got a precisely drilled hole, precisely perpendicular to the machined face, and then I'm indicating, or indexing I should say, on a precision turned pin that is pressed into a precision hole, and then I'm going to put the hold down screws, and then this operation is going to machine the outer faces, making them perpendicular to the reference face. Okay, boy, that tool just spits coolant. Wow, what a mess. I said before in previous videos that I custom designed this splash guard. I don't really want a totally enclosed machine. I like the visibility, but it sure is a pain when I'm using certain cutters that just spit coolant. So the first cut that's going to be made here is a counter bore in the surface of the part, followed by going around the outside and cleaning up the outside edges. Now that's looking very nice. That Z feed looks way too slow. I'm going to go speed up that Z feed, but here's the, also going to add a y-axis move to clear so I can get my cordless drill. So now the faces have been milled perpendicular to the reference surface. I have a reamed hole with a nice counter bore, the attachment holes, and then the third operation will be a couple of mounting holes on one of the faces. So that pretty much concludes the first two operations in the video. I'm going to go modify the tool path, set up the combo tool path that does both in one load cycle, and then I'll turn off the cameras, turn the cameras back on when it comes time to drill and tap those last two holes. And wow, this is a simple part compared to the previous ones. So the first and second operations have now been completed. And one thing that I didn't mention that's also being accomplished with this setup is that the counter bore depth is also precisely controlled, because if the Z reference is on the bottom, the counterbore depth will be referenced to the bottom, and of course the critical depth is from the reference surface, which is in contact with the tooling plate, and so that makes sure that the surface of the counterbore, where the bearing is pressed down onto, make sure that that dimension is correct as well. So for people who are curious about machining or learning machining, it's really important to know where your reference surfaces are. Where is zero? What face is square? What face is perpendicular? And don't get confused thinking that, oh, the mill surface is going to be flat. Well, sometimes it is, sometimes it isn't. And don't assume that, oh, the cut that you made on the saw is going to be perpendicular. It probably isn't, unless you have a really, really, really accurately set up saw that cuts well, and then you've checked it and verified with a precision square. But just in general, keeping track of reference surfaces and measurement, just about the most important thing you can do in machining. So I'm going to start the third operation here, which is a power tapping operation, 2 holes, and standard operating procedure. Even though it's a trusted program, I'm going to treat it as the first time it was ever run. And just absolutely sure here, I know I did it, but you know, when I'm thinking about other things, it's so easy to make a mistake. Single step mode, verify the 1-inch pre-feed height, verify, I actually have a part from the previous run that I can verify, yep, quick sanity check. The part is inserted in the vise correctly. And of course I have notated on my setup sheet how the part should be put into the vise, but it never hurts to double check, triple check, check again, check to check. Going to be a couple of 832 tap holes. Probably could be a fast tech cycle, but we're not going to change it. Okay. And as I said in the previous video, I typically drill my blind holes substantially deeper than they need to be, just to make absolutely sure that the tap doesn't bottom out, the chips don't get caught. I'm using a spiral fluted tap, and the spiral fluted tap ejects the chips up out of the hole, which works really well for blind holes. Tapping at 250 RPM with the Tormach compression tension tapping head. The Tormach doesn't have an encoder on the spindle. It doesn't know precisely how fast the spindle is rotating, and so it can't do true rigid power tapping, but this workaround, by putting a little bit of spring load in the compression tension head, the machine gets as close as it can and the head takes up the error. So here we go. All is looking well. I'm going to carefully clear the chip. Even though the chip does eject out of the top of the tap, the cleaner the better. So that concludes the machining operation on this part. I'm going to finish the rest of the run off camera and then pop them in the vibratory finisher. and move on to the next part. So thank you for watching.